All right, were there any questions? We're in day 11. No questions? We're going to have to go kind of dark here again. I've got a lot of graphs to show you today. Good night. See you. I'll wake you up in an hour and 40 minutes. All right, so we're really kind of finally gotten to what the whole point of all of this is. All right, so I think things are going to pick up pretty quick from this point on. The material is going to be significant, and there's a lot. Like the directional derivative, very mechanical. You just go home, you take the derivative, and it's not a lot to it. Here, as you're going to see, we're going to run into a lot of algebra. We're going to run into a lot of things from the past. So it makes these problems take a long time, and not every problem is so uniquely different from the other one that you have to treat every problem. You can't just carbon copy something else. All right, so just be prepared for that. So we're going to start with the idea of maximum and minimum values. All right. And we're just going to do a quick review of Cal 1. Those are the sections in the book that I'm talking about, 4.1 and 4.3. And we're just going to discuss, I did this already with you. I discussed max and mins because you needed it on your on the last take-home quiz. But there were a few results from Cal 1, just right up here, yeah. Said in Cal 1, if we have a function, right? Nice continuous function. Then it has these points that we would refer to as being local max and local minimum points, correct? They may not be the highest point on the graph, but locally they are. It's like this point's like king of the hill, right? Anywhere around here, there's no point higher than that one. Same thing here. This is locally, it's the lowest point. Same thing here. Locally, it's the highest. So the way that we found these in Cal 1 is we employed what was called the second derivative test. Let me make sure my phone's quiet. We employed the second derivative test. So what it said, second derivative test, says if f prime at some point c equals 0, and f double prime at c is greater than 0, then what was the conclusion? Anyone remember? You would have a minimum there, a local minimum. Okay, now the graph of this, the idea here is I'm just going to draw act like this is a graph. Well, I'll do it a different way. What we're saying is that at some point, our first derivative is 0, meant that we had a flat tangent line there, right? And then the second derivative being positive meant we're concave up, which means our graph must look like this. Boy, I missed that pretty bad there. Okay, so the only way we can be flat here and be concave up is if we have a local minimum there. So it looks like this point right here. So the result here is then F of C is a local minimum. Okay, that's the first part of the second derivative test. It said also if the first derivative was 0 and the second derivative was negative at some point, then we have local max, right? Okay, that's the Cal 1 result. First derivative is 0. Second derivative is concave down, right? It tells us it's concave down, so we have a local max there. Now, the second derivative test does not guarantee us we'll always be able to find local maxes and local mins. Because what if you had a situation like this? What if you had a graph that did that? Then the point up here would be what? A local, would that be a local anything? You're still continuous here because you can draw this without picking up your pencil. You're not differentiable there, though, because you have a cusp. But is that a local maximum? Yes, it is the highest point in that little neighborhood around it. It's the king of the mountain. The problem is second derivative test won't work here because the first part of the second derivative test says you have to have the first derivative is 0 there, right? And the derivative at this point would not exist because you have a cusp. So although the second derivative test is good at getting us local max and minimums, sometimes it fails to identify all of them. So the way that we would approach this is to, how would you do this? How would you figure out that you had something like that going on there? Okay. Tell me about the derivative there. What's the derivative at this point? I'm going to call that point C. What's the derivative there? Undefined, right? I'm just going to put UND, undefined, or does not exist, derivative doesn't exist there, right? Then what you could do, if you know that your derivative is undefined somewhere, then what you could do is you could pick some test points to the left and to the right of that point, and let's say plug that point in and check what the derivative is there. What's the derivative at this left point? It's a positive number because you have a positive slope, right? And then the derivative over here would be a negative number. And so you know that what's happening is you're going up and then you're coming down, so that means you must have a local max there. So this was another way of doing local max and local mins without the second derivative test. Just want to remind you of how this worked, okay? You'd be looking for a change in sign in the derivative. All right, now today, we're going to use something like that, but now we're going to be looking at surfaces. If we take a surface like this, right, we've got these mounds and these little valleys, right? This particular surface, it looks like we do have some highest points and lowest points, and then we have some locally high points and low points, right? Like you could be the king of this hill, and then someone could be the king of that hill, right? This one looks like it would be the maximum of everything, though, right? So it'd be like a global maximum or a global extreme. If I zoom in a little bit and take a look at it, right? Now, we have some language that we want. Now, this is straight out of the book. That's the same picture here, okay? We have a local maximum versus what we call an absolute maximum, or sometimes books will call it a global maximum. We understand the difference? Is this one here a local maximum? Yes, but it's also the absolute maximum. And then you have local minimum and absolute minimum. So this is what it means to be a local maximum. This basically just says that to be a local max, at a point, that point right here, f of AB, has to be bigger than all the ones around it. And then to be local max, local minimum, it's the other way around. That point, f of AB, has to be smaller than everything around it. All right, that makes sense. Okay, then we have a theorem that tells us if f has a local maximum or minimum, if it does, at some point AB, and the first order partial derivatives exist. So if we can take partial derivatives, and those partial derivatives are nice functions, then the partials will both be equal to 0. Now this is an important theorem that we understand what's being said here. First of all, it's saying if there's a max or min, if there's a local max or a min, if there is one, all right, and, so this condition also has to be held, and the partials exist at that point, then the partials have to be 0. Understand? It's kind of like this scenario here. Does this function have a local maximum? Yes? Does the derivative exist? No. But it still has a maximum, right? That's what this theorem is saying. It's saying if you have a maximum and the derivatives exist, then the derivatives have to be 0. Well, that's kind of like this case. If the derivative exists, right, then it's got to be a local max or a local min. Or I should, no, hold on. If the derivative is, if you have a local max, let me go to this one. If you have a local max and the derivative exists, the derivative must be 0. Okay, now that's going to lead us to what's called the second derivatives test for surfaces. And this is the main thing of today. This is what we're going to spend all of the rest of class on, is doing examples using this test right here. It says, suppose the second partial derivatives of f are continuous on a disk with center AB. So you have a function, the second partials have to exist, which means that the first partials had to exist, right? Okay, so your second partials exist in this little neighborhood, okay, a disk around some point. And suppose that the partial with respect to x and the partial with respect to y are both 0. All right? So if that happens, then here's what we know. We can compute this thing that we're going to call d. Don't confuse the d with the directional derivative, all right? This d is going to be computed by taking the second partial, I know this is hard to read, but second partial with respect to x, evaluated at the point, times the second partial with respect to y, evaluated at the point, minus the partial with respect to x, then y, evaluated at that point, then squared, then just compute that. All right, so that's going to give you a number. When we compute this d, we're going to get a number. And then we have 3 possible results. If the d that we compute is positive, and the second partial with respect to x is also positive, we know that we are at a local minimum. If the d is positive and the second partial with respect to x is negative, then we're at a local max. And if d turns out to be negative right away, it's not a local max or a local minimum. We're actually going to call that a saddle point. All right, so because we're going to use this formula all day, I think what I'll do you mind pulling up the blinds a little bit there so we can have a little bit of light? There we go, that's good. That's what we're computing. And then I'll put over here what the results are. If we have d is positive and second partial with respect to x is positive, we'll have a local min. If d is positive, second partial with respect to x is negative, we have a local max. And if d is negative, we have what we call a saddle point. And what if d is 0? Didn't give us that scenario. What do you think? Local max, local min, saddle. This is the worst scenario we could have. It means the test fails, all right? It means we won't be able to figure out what's happening. Well, we might, but not with this test. So the test is inconclusive if you ever get 0. Now, we're not going to get into the actual why is it work this way, because like on this one, it was kind of easy to show you that, look, if the derivative is 0 and we're concave up, right, then that has to be a min. And here, if we're derivative is 0 and concave down, then it has to be a max. It's a little more difficult to understand what's happening here, because we're computing this thing, and I mean, what is all this, right? So let's not get into that. If you want to, we can sit down, go through it in my office. I can kind of try and give you some geometric reasoning to it, or you can try and reason it yourself. I don't remember if the book shows why it works, but no? Did someone say it doesn't? Oh. Okay. All right, so here we go. We're ready. We now have a technique for trying to find local maxes and local mins for a surface. So our first example is I say find the extreme value. So I'm saying find the local max and local min of this function. Well, let's look at it first. Now, remember, in general, you won't have the picture, will you? Does it look like we have any local maximums? Does it look like we have any local minimums? It looks like a saddle point. See the origin right there, the center point? You can't say that's a local max because the sides come up, right? You can't say it's a local min because these sides this way go down. But it looks like a saddle, doesn't it? One way it goes down, the other way it comes up. That's like a saddle. That's why we call it a saddle point. We should get a saddle point here. Let's just do the math, though, and see how things work out. All right? So my function is the function f of x, y equals y squared minus x squared. All right. We are going to need to figure out a couple of things here. The first part of this test says, suppose second partial derivatives of this exist at some point a, b. Suppose that the derivatives at the first partials are both equal to 0 at this point. I need to figure out that point, the a, b, that make these two partials 0. Once I figure out what the point is, then I can go figure out what d is. But the first step is to figure out what the point AB is. Understand? So to do it, I just need to take each of the partials, partial with respect to x, partial with respect to y, set them equal to 0, and then try and solve it algebraically. So I'm going to take the partial with respect to x first. What is that? Negative 2x. Then I'm going to take the partial with I'll do it next to it. Partial with respect to y, that's 2y. And now, in order for me to find this point AB, I need to set each of those equal to 0. So setting the first partial equal to 0 means that I set negative 2x equal to 0, and that has a pretty simple solution, right? Yes, x is 0. Now, the other one is just as clean. Setting the partial with respect to y equal to 0 means that 2y must be 0, so y must be 0. So the point that I have, right, my AB in this problem is the point 0, 0, right? That's my AB. Now I need to compute D. So D of AB is going to be the second partial with respect to x evaluated at that point times the second partial with respect to y evaluated at that point minus the partial with respect to x, then y, and then evaluated at that point, squared and subtracted. All right. So since I'm going to need those partials, let me go get those partials over here on the side. What's the second partial with respect to x? Negative 2. What's the second partial with respect to y? 2. What's the partial with respect to x followed by y? 0. Now, those three things that I just got, I'm supposed to take those and plug in what point? 0, 0. But do you see that those things don't have x and y in them? So it actually turns out for this particular, this is probably the only problem it's ever going to happen for, is that these second partials actually do not depend on x and y at all. So we actually could have computed D without having it, without having the 0, 0 point. But we're still going to compute D. All right, so let's get D. D is going to be, D of 0, 0 will be the second partial with respect to x at 0, 0 times the second partial with respect to y at 0, 0 minus the partial with partial with respect to x, then y at 0, 0, all of that squared. But we just said that that's, what's this? Negative 2 times this one. 2 minus 0 squared is 0. 2 times negative 2 is negative 4, which is less than 0, right? Our D is less than 0. D is less than 0 means what? Saddle point. So we have a saddle point where? At the origin, right? At the origin. So watch the way I write this. I have a saddle point at 0, 0. Now remember, the surface is in three-dimensional space, right? So the point, I need the third component. What's the third, not component, the third coordinate of the point? You just come up here and plug 0, 0 in here and you get 0, right? So it turns out to be 0, 0, 0. And that is confirmed with the picture, right? We were all in agreement that it looked like the origin was where we had the saddle point. Any questions? What? Because if we go back to this picture and I say, where's the saddle point? Where is it? If you say, okay, it's right there, right? What is that point? You can't tell me it's 0, 0 because 0, 0 is two-dimensional. It's the ground, right? I want the actual point on the surface. So it's 0, 0, and then the third coordinate would be the z coordinate, which would be 0. Yes? Yeah, f of x, y. You're basically plugging in 0, 0 right here, right? On this one, as you can see here with this one, your points that we're going to get are not going to be at the origin, okay? All right, so let's try this one. Here's the function. Looks like we have what here? What does it look like we have to you? What does it look like? We will get. What should we get? 2 local minimums and maybe a saddle? Where are you seeing the saddle? Like in the middle there? Y'all see that? Now we have to act like we don't have the picture, right? Because you won't have the picture in general. The picture is just to help us see what's happening, like connect the math we're doing to the visual of what's happening. All right, so here we go. Our function f of xy equals x to the fourth plus y to the fourth minus 4xy plus 1. I hope that you, in some sense here, understand the magnitude of what we're able to do right now. I mean, someone gives you a function, a surface. We're actually able to figure out the highest and lowest points on the surface. That's a big deal, because even in Cal 1, finding the highest and lowest points on a graph was like one of the main results. I mean, that's what we were trying to do, right? So now we can do it for surfaces, and we're going to learn later we can do it for other things too. It doesn't have to be a surface. It can be in dimensions that we can't see. All right. So you kind of start to get into a rhythm here. You realize that to do the problem, you're going to need the partial with respect to x, the partial with respect to y, the second partial with respect to x, so with respect twice, right? This partial with respect to y twice, and you're going to need the partial with respect to x and y. Aren't you going to need all those? So you might want to start the problem off by doing all those right off the bat and getting them all together, and then start using them as you need them. Or you might just want to work through it, as you need them, get them. It's really up to you. Understand what I'm saying, though? So I'm going to go ahead and just start and get all my partials in order. I'm not afraid of taking partials here because this is a polynomial, and the partial derivative of a polynomial should be pretty clean. So what's the partial with respect to x? 4x cubed minus 4y. Okay, let's do the partial with respect to x again, because we're going to need it later. 12x squared, okay. How about the partial with respect to y? 4y cubed minus 4x. How about the partial with respect to y again? 12y squared. And how about that partial with respect to x followed by y? Negative 4. Those are all the derivatives I'm going to need in order to do this, right? So the first thing I need to do is after I do that, the next thing I need to do is find the AB, right? Find the point that we're talking about, right? So how do I figure out what AB is? Okay, good. So I set fx equal to 0, and then I'll come over here and I'll set fy. Is it okay if I say fx, fy? You all understand what I'm saying? If I want the second partial, say fxx, that's okay? All right. So fx is 0, so that means I'm going to set 4x cubed minus 4y equal to 0. And then on the other one, or no, I'll just leave it there. What can you tell me about this equation? I mean, what's that? X cubed equals y. So you can't give me an exact answer, right? Like in the previous problem, it was x was 0, wasn't it? We were done? Here, you have one equation and two variables. You cannot solve for a unique solution here, can you? You can only get a relationship between x and y. So I believe you move the 4y over divided by 4? Yes? Everyone okay with that? All right, so we do that, we get this relationship. I know x cubed must be y. Well, that doesn't give me any answer, but let me go to the other information, all right? I need that other partial, f partial with respect to y, to be equal to 0. So set that other one, 4y cubed minus 4x must be 0. And what could you tell me about this? Y cubed must be x. Again, you can't solve for that uniquely because you have one equation, two variables. However, you need both of these to be true at the same time, don't you? You need the AB to work for both of those at the same time. So what can you do? Okay, you can take this y here, right? and plug it in right there for that, right? On the other equation. Or you could have done it the other way around. You could have taken this x right here and plugged it in over here. Either way, I'm going to go with the y. What I'm going to do is I'm come to this equation over here. I'm going to replace y with what? X cubed. So that becomes x cubed, but then cubed again, right? Equals x. Yeah? X cubed. That y is x cubed. So you plug it in, then you cube it. So x cubed cubed. What's x cubed cubed? X to the ninth equals x. And now we have an equation that has one variable. And one equation, one variable. We hope to get a solution, or possibly more than one. So I'm going to ask you what to do because there's a common mistake here, and I want to see if you're going to make the common mistake or not. Because we're here to learn, right? It's okay to make a mistake now. You just want to make it on the test? Divide by x? Yay or nay? Why not? You get what? That's right. There's only one issue when you divide both sides by x, and that's what if x is 0? And look, isn't 0 a solution to this? If x is 0, isn't that a solution? If you divide through by x, you're going to lose that solution. So the standard way to do this, all right, so to totally avoid all of that possible chaos, is to take this equation and move everything to one side. Okay? Move that x back to the left side, and you get x to the ninth minus x equals 0. Do you agree that I haven't changed anything? I don't have to worry about dividing by x anymore, right? Now on the left side, factor out a GCF. So factor out x. You're left with x to the 8th minus 1, aren't you? The zero factor property says that if I factor something, and those factors multiply to be 0, I can set each of those factors equal to 0, can't I? All right, so I set this equal to 0. I set the other one equal to 0. The first one, the solution is there, isn't it? The other one, how can you do this one? There's a couple of options, but what do y'all think? Move the one over and then 8th root. Does that seem legitimate? Yes? Because you don't have to worry about dividing by 0 there. Or you could do what? Yeah, difference of squares, and then it would go again difference of squares, and then it would go again difference of squares. It'd be multiple applications of difference of squares. But the easier way is just x to the 8th equals 1. Now the 8th root, now you have to be careful, right? Because when you take the 8th root, what do you have to do? Plus or minus, right? You always do plus or minus whenever you come in and you take an even root on both sides, right? Odd root, you don't have to worry about that. Even, you do. All right, so we're going to get 8th root of 1 is 1, right? And so we get x on the left side equals plus or minus 1. We have a total of how many solutions? 3, right? We have 3 values for x. So let's list them out here on the left side. Or, yeah, I can do them to the right of it. I got that x must be 0, x must be 1, or x must be negative 1, right? But then, from each of those, what's y? Well, remember, what was the equation for y here? Y was x cubed, wasn't it? So just cube each of these answers. You get 0. They're identical, aren't they? Y is 1 times 1 times 1 is still 1. And then here, you get negative 1 times negative 1 times negative 1 is still negative 1. So now we have 3 potential points, right? 3 potential points that we have to check The points are the points 0, 0, 1, 1, and negative 1, negative 1. Those are my ABs, so to speak. Remember, our goal was to try and figure out what the AB was? We have more than one, which makes sense, right, with the picture? We should have had, well, we said at least we had two local mins, didn't we? And there was a question about that saddle point. Maybe it was, maybe it wasn't. Well, the fact that we have 3 makes me think that that one is a saddle point, but the only way to know is to compute D. So we go compute D now for each of those points. All this making sense? What's going to get more challenging is the algebra within the problem. All right, that's what's going to get more difficult. Is this part right here, solving this, figuring that out, that's going to become the challenge. As far as the method is always the same for each one. All right, so let's go. I need D of 0, 0. Remember, that's f x x at 0, 0, f y y at 0, 0, minus, in brackets, f x y at 0, 0, all that squared. I need to go back to my other page to get these. fxx, if I plug in 0 for x, right, I get 0. If I plug in fyy, if I plug in 0, I get 0. So I'm going to come back to this right now real quick. I know that this is 0 times 0 minus, now I do need to make sure that this is not 0. Because if it's 0, I get 0 and the test is inconclusive, isn't it? But what's fxy? It's negative what? Negative 4? But then I'm going to square it, right? So when I square negative 4, I get 16, and I'm subtracting 16 from 0, so I get negative 16, don't I? And that is less than 0. Therefore, I have a saddle point, right? I have a saddle point. Where's my saddle point? 0, 0, and then go get that z coordinate. Where do I get that again? Plug it into the original function. So if I plug in 0, 0 in here, what do I get? 1. So if I go to that point on the surface, it should be a saddle point. Now we have to do the same thing for 1, 1, and same thing for negative 1, negative 1. D of 1, 1. Now I'm not going to write out what it is, right? In other words, I'm not going to write this part of it out again, okay? Is that all right? I'm just going to go straight to the numbers. All right, so what happens when I plug in 1 into fxx? 12. And into fyy? 12. So I have 12 and 12. 12 times 12 minus fxy was a constant, wasn't it? Or no, was it? It was negative 4. fxy was a constant, negative 4. So I don't have to worry about computing that. So negative 4 squared. And I can already tell you right there, that's positive, isn't it? 144, take away 16, it's still a positive number. So what does positive tell me? Well, there's two possibilities, right? There's two possibilities with D being positive. So what I then need to go look at is that fxx we had. So now just focus your attention on fxx. Where was it? fxx is this first one right here, isn't it? Wasn't that the one? 12? That 12 is positive, isn't it? If your fxx is positive, you have a local min. That's right. So D being negative, right away, your saddle point, you have to do anything else. But if D is positive, now you have to refer to a second piece of information, which is just this first number here. If that number is positive, then you're at a local min. If it's negative, you're at a local max. Okay? So this means that f(x(x) is positive. And of course, this right here meant that d was positive, and therefore we have this condition. Therefore, we have a local minimum at the point 1, 1, and yes, go get the z coordinate. It's 0? 1 here, 1 here. 1, 1. What, negative 1? Negative 1? And do I need to show the work for the next one? Or can I just tell you what it is? It actually works out exactly the same because you're plugging negative 1 in, but f(x(x) was 12x squared. So when you square the negative 1, it's still 12. So it comes out to be exactly the same. So without the work, d of negative 1, negative 1, 12 times 12 minus 16 greater than 0. This guy right here is greater than 0. And so we have a local min at negative 1, negative 1, 1. Is it negative 1, negative 1, 1? Yeah, should be negative, hold on, sorry, negative 1. This one right here? Yes. We have a local min at negative 1, negative 1, negative 1. So on a test or something like that, you would either need to come in here and box these results so I could see your answers, or just rewrite them or summarize them. You know, make a little table on the side and put them all together in one thing and box them up. Make it easy for me to find them. Okay, what's your final result? Local min, local max, saddle. I can see it real easily. Questions? Yes. Looking from the top. Okay, so we're looking from the top here. Remember, let's see. Oh, that should say 1, 1. I don't know why that doesn't say it. So if we go, my graph's all turned around. Okay, now looking from the top. It may not let me. Okay, there we go. If you go out x1, y1, right? And then you go look at the actual value of the function there. We're down, you see we're down below the xy plane, so we're down 1, negative 1. That's actually a lowest point, and it matches up to that point there. See? And then the same thing with the other one is on this end. And then our saddle is right there in the middle. Okay? Wow, this is a weird looking graph here. This is kind of cool looking, don't you think? Would Okay, our function x cubed y plus 12x squared minus 8, and that's it. Now, again, I'm going to start doing partials. Because it's a polynomial function, it should be pretty clean taking all these partials. Now, compare that to what I'm trying to get you to see is this. Like, look at this function here. the partials might start getting ugly here. So you may just want to start with your first partials first and then work your way through the problem. Take the other partials when you need them. This one, again, the partials might get pretty ugly. That one might get ugly. That one definitely gets ugly. Okay? So one thing at a time. I'm gonna go through and just knock this one out. Knock all the partials out first. Partial with respect to x, 3x squared y plus 24x. Partial with respect to x again, 6xy plus 24. Partial with respect to y is x cubed minus 8. Partial with respect to y again is what? 0. Partial with respect to x followed by y is 3x squared. Okay. Making sure we're all on board. All right, those are all my partials. Now I'm going to try and find the AB. So I'm going to take each of the first partials and set them equal to 0. When you do your work, you don't have to follow the way I'm doing this with these columns. You just do it however you feel comfortable. I'm just trying to fit it all on one screen so I don't have to keep scrolling. All right. All right, this first one, 3x squared y plus 24x must be 0, right? Now, I already know by looking at that I'm not going to be able to find a unique solution necessarily because I have two equations, two unknowns. One equation, two unknowns. So I may not be able to get an exact answer too quickly there. However, I did notice when I took that second partial with respect to y, or that partial with respect to y, I got x cubed equals minus 8 equals 0, right? That's what I'm going to get. And that's a very clean equation, isn't it? And so I can just solve that. I can move the 8 to the other side. I can take the cube root, which means I don't have to do plus or minus, right? So I only get one solution. The solution is 2. We agree? Now, remember, the point that we find, right, the AB, we know we can have more than one point. The AB that we find, though, whatever it is, whatever makes this one true, right, if x has to be 2 to make this one true, that means over here, x also has to be 2, because it has to simultaneously make them true. So now what I can do is I can come into this equation and replace that x with 2. That's going to make my life a lot easier. So coming in here, letting x become 2, we're going to become, what, 12y plus 48 equals 0. All right. So what's y? Negative 4? Solve that linear equation. So we only have one point, don't we? Right? Just one point to worry about. The point that we have, our AB in this problem, is the point, make sure you get the order correct, 2, negative 4. So I'm going to now compute D at that point, 2, negative 4. It is, what's fxx at 2, negative 4? Well, I might have to actually work this one out. Let's see. I can see it right here. I'm going to plug in 2, negative 4 right here, right? 2 times negative 4 is negative 8 times 6 is negative 48 plus 24, negative 24. And then fyy is 0. So I didn't even have to really do well, did I need fxx? I might have needed it later, right? If D turned out to be positive, I might have needed it. It's not going to happen in this case, but do you see what I'm saying? We still may have needed that actual number, so. Yeah, if D would have been positive, we still would have had to have gone back and looked at what this number was. I could tell what? That what wasn't going to be positive. D, yes. Because that minus whatever square is always going to be negative, yes. So what is fxy at the point 2? Just so we have it, okay? What is this last part here? 12, right? 12 squared? And this whole thing is negative, which means we have a saddle, right? So I have a saddle point at the point 2, -4, and then you've got to go plug that in. And I'm going to save myself some time. It's 2, -448. So this function does not have any local max or local max or mins. It's hard to see where that saddle point is on here, isn't it? I don't know. Well, it's right there. Did y'all see it pop up right there? That's where it is. There's only one. All right, this next one is pretty nasty here. This is the the pimple function. It's just a little mound right there. There it is. Just a single little raised bump. Question? Huh? Y'all got a question or anything, Ben? You're good? Okay. Find the local maximum minimum values and the saddle points of f of x, y equals e to the 4y minus x squared minus y squared. All right. Tear out a sheet of paper. Now, this can be a quick quiz, 5-minute quiz. Not even 5 minutes. It's going to be like a 2-minute quiz. Just put your name on it. Don't get all upset. All I want are the two first partials. Partial with respect to x, partial with respect to y. That's it. Not fxx, not fyy. I just want partial with respect to x, partial with respect to y. And then bring it up, and we'll move on. What do you think? 3 minutes enough time? Do your own work. Just these two, right there. That's all I want. Fx and Fy. Just start a new pile, please. Let's see. Jose, Dan, Patrick. Uh-huh. Tamara. Chris Schaefer? Chris? Yes, sir. It's Thomas. This is your take home. Jose Aguilar? I think it's out of 100 points that, so if it says like -5, you got a 95. Gregorio. Ali. Joshua M. Okay, Diego. Thomas Hernandez. This is another one. Yeah, just your name. Set it up there. Joel Acuna, right here. Raul. Jose Rojas. Chris Schaefer. Jose Aguilar. Tamara. Joshua Shaw, not here. Joshua M. Dan. Chris Schaefer. Josh M. Diego, I'm going through my stuff and I just realized that your quiz 4, I didn't grade it. It got shuffled into the back, so I'm going to have to grade it, okay? I'll get it back to you. So if online it says you have like a 0 or something, don't worry about that. Okay. All right, anyone else? All right, that quiz is hopefully is just to kind of inflate your grade a little bit. Let's see. The derivative of e to anything is itself, right? Then times the derivative of what's up there with respect to x. What's the derivative of what's up there with respect to x? -2x. So I could just move that out in front of the e to the stuff, right? That's it. And then same thing for with respect to y. It would be e to that stuff and then times the derivative of what's up there with respect to y, which would be 4 minus 2y, correct? And I need that in parentheses because it's 2 terms. That's it. All right. Now, I'm also supposed to go get fxx, fyy, and fxy. Do you see why I'm not real happy about going and doing that at this point? Because to do fxx, I'm going to have to do what here? Product rule. There's a product, right? I have like -2x times e to something. I have to apply the product rule. And then here, same thing on the product rule. So what I'm going to do is I'm going to choose to, at this point, not mess with that yet. And I'm going to just go figure out what makes both of these 0. Maybe I'll get lucky and there is no point that makes them 0. Yes? With respect to y, you mean? Yeah, if I go with respect to x, then y, then I would not need product rule. Correct. So that one will be a little easier. But so let me go to the setting of these equal to 0. If I set partial with respect to x equal to 0, then that's going to mean I'm setting -2x e to the 4y minus x squared minus y squared equal to 0, right? Now, as ugly as that looks, what do we know about this? Say again? It's 0 when x is 0? Okay, what about all this stuff? Why doesn't this matter? E to anything, right, cannot be 0. Yes? That's the point I want to make sure everyone's clear on. E to anything can never achieve the value 0. So what I'm actually doing is I'm saying, oh, look, I have the factor rule. I'm setting each of those equal to 0, right? Negative 2x equal to 0. I'm setting all this junk right here equal to 0. That can't happen. The only way this one happens is if x is 0. Well, that's nice. I'm happy with that. Then I also have to go figure out when is the partial with respect to y equal to 0. Well, that's kind of the same story, right? I have this 4 minus 2y e to all this junk equals 0, right? E to the junk can never be 0, so I just have to take 4 minus 2y and equal it equal to 0, right? Equal it equal to 0. And equate it to 0. And that gives me y is 2, right? Well, the good news, if there's good news, is that there is only one point I have to compute d at, right? There's only one point. It's the point 0, 2. The problem is that I still do need to get those partials, don't I? Right? I need fxx, I need fyy, I need fxy. So here we go. We got to get them. Do I? I thought you were suggesting something, no? All right, I'll try and squeeze fxx up here. fxx, product rule. Our product is right here, right? So the derivative of this one is negative 2 times this. So is it all right if I write it this way? Negative 2 e to the junk. And then product rule says plus the derivative of e to the junk. What's the derivative of this? It's this, right? This whole thing again, right? So that's negative 2x e to the, I'm going to get even more lazy, e to the j. All right? And then, what do I still have there? Remember, finish the product rule off. Times the negative 2x. Product rule. Derivative of this times this is this one, and then derivative of this, which is this, times this, which is this. All right. I can clean that up a little bit. Do you agree with that? And these both have, what, a 2 and an e to the junk in them? I can pull a 2e to the junk out and be left with 2x squared minus 1. I just rearranged things here. The 4x squared, I'd pulled a 2 out, so there it is, and I pulled a 2 out of this and left me with a negative 1. That's kind of a clean version of fxx, isn't it? Okay. Now we need fyy. I'm trying to do it where I can refer back to it. So fyy is right up here. So product rule again, derivative of this first one is negative 2 times e to the junk plus what's derivative of e to the junk? With respect to y again is this again, right? But then finishing off the product rule, I have that again also. So wouldn't it be 4 minus 2y what? Squared e to the junk? Did y'all follow what I did or not with this? Yeah, derivative of this is exactly what this was already. And then I have to tack onto that with the product rule this. So I wind up squaring that one. All right, I could clean that up, but I'm not going to. All right, what about fxy? So going back up to this one, if I'm treating this derivative with respect to y, this negative 2x, like was said, is a constant, so I don't need to worry about it. So what's the derivative of all this with respect to y? It's this, right? Right here. And then just tack the negative 2x onto the front. So it's this with negative 2x in front. Yeah, I'm there. I'll bring that fxx down here so I have them all side by side. All right, so that's what I need, those three things. Now let's get D. So for D, I'm actually going to the point, what, 0, 2? What's fxx at 0? Oh, man. At 0, 2? 0. Gone, right? It's gone? Right? 0, 2? Oh, wait, no, I'm plugging in the wrong thing. Hold on. That's why you were looking at it like that, Alan, right? Okay, this is the one I meant to plug it into. All right, so that's not so simple. All right, what, I need to take the junk and figure out what happens when I plug 0, 2 into the junk. I finally need to go back and figure it out. So let's look back up here. Here's the junk, right? What if I plug in 0 for x and 2 for y? What would happen? This is gone. This 8, and then take away 2 squared is 4, so e to the 4th? Yes? E to the 4th? All right, so when I plug in 0, 2, this is going to be 2 e to the 4th, right? 2 e to the 4th, and then we're plugging in what here? 0 and then minus 1, so negative 1. So just make that a negative. Negative 2 e to the 4th. Do y'all agree? Then let's plug in 0, 2 into fyy. We already know this e to the junk is going to be what? E to the 4th? E to the 4th? E to the 4th? So really what's happening right here is what's important. This goes to 0. This one is 0, right? So that's 0. And then we just have negative 2 e to the junk. So negative 2 e to the 4th again. Minus, now this is the one, fxy, when we plugged in 0, 2, we got 0, didn't we? This d, when I compute it, I don't care about the numerical value. I can tell by looking at it, it's positive, right? Negative number times a negative number is positive. This is greater than 0. If it's greater than 0, I either have a local max or a local min. To figure it out, I just need to look at the fxx part. And that was what? Negative. So I am looking at a local max. Local max at the point 0, 2, and then come up here and plug in 0, 2 into this. We did that already, right? E to the 4th. What do you all think? Seem okay or not? What's today? 29? No, today's the 1st. Okay. We're going to keep moving. I think the next one's worth going through. It's a good one. All right, so our function's x squared plus y squared plus 1 over x squared y squared. This is a really, I think it's a really cool graph. You have these asymptotes. Y'all see those? Where is this thing not defined? Domain-wise, what can you not plug into this? X can't be 0, and Y can't be 0, right? So you can't plug anything on the x-axis in, can't plug in anything on the y-axis, which you can kind of see, right? But then what's happening as you get closer to the x and y-axis is that it's becoming asymptotic. And so you've got these asymptotes. So I think it's a cool picture. But you can kind of see maybe when I look at it from the bottom, it looks like we've got some local minimums down there, right? Down in there. Hard to see. There they are, though. There's 4 of them. Where are they? What are they? Now, that's the first thing I'm going to do to change the problem. Y'all see what I did there? That's just going to make my derivative easier rather than having to worry about like quotient rule or something like that. Let me try and get all my derivatives. Fx is 2x, then what? Negative 2x to the negative 3, y to the negative 2. So the power on x comes out, right? You subtract 1. All right, what's fxx? 2 plus 6 x to the negative 4, y to the negative 2. Y'all okay with that? I keep asking if you're okay with it because last class I know we had some issues with partials. Are we all right now? Yeah. Okay, good. Fy, very close to the fx, right? 2y minus 2x squared, no, x to the negative 2, y to the negative 3. Fyy is 2 plus 6x to the negative 2, y to the negative 4. And then what's fxy? So taking derivative of this one up here with respect to y, that's gone, right? Here, the y, you bring the negative 2 down, it becomes what? 4 x to the negative 3, y to the negative 3. Are we all on the same page here? All right. Now the fun part. You've got to figure out your AB. And we're going to have 4 of them, but we don't know that. We're acting like we don't know that, right? So let's see if we can figure out what they are. So I'm going to take my first partial with respect to x, set it equal to 0. That means I have to take 2x minus 2x to the negative 3, y to the negative 2, set it equal to 0. And then the other one, uh, 2y minus 2x to the negative 2, y to the negative 3. Set that equal to 0. Any ideas? Solve for x, solve for what? We know x is 1, what? Is y 1? How do we know y is 1? Wait, hold on. Which one are you working with? And do what? Oh, you move this one over and divided both sides by, well, factor. It's good. Y'all sound like y'all have got ideas. That's a good thing. Yeah, there's a lot of things. This is good. I'm glad to hear so much chatter because it's a good thing. This is the challenge for you, is that this is algebra at this point now, right? I mean, really, the calculus part of this is done. It's now algebra, but we've got these equations with multiple variables. So we can approach it different ways. I'm not saying, no, don't do it that way, don't do it that way. As long as you don't break a rule, you're good to go. I'm just going to show you the way that I would approach it, and then you either like it or don't like it. I don't know. So the way that I would approach this is I would have probably rewritten those negative exponents as positive exponents, just to be very clear on what I've got here. So drop them down. Then I probably would have moved that to the other side and made it 2x equals 2 over x cubed y squared. And then maybe I would have multiplied both sides by x cubed y squared. But if you do that, what do you have to promise me? If you multiply both sides of an equation by something, you have to promise me that you're not going to do something. That's right, that x can't be 0 or y can't be 0, right? Same thing when we divide by x. We can't do that, because it eliminates the possibility of x being 0 or y being 0. Do I have to worry about it here, though? Do I have to worry about multiplying both sides by x, y? Why not? That's right. Our original function isn't even defined as 0. That's a subtle thing here, but very important. Because, look, where we're going with this, the next section, the algebra is even more intense, and you have to get everything under, I'm not saying this is intense, I'm just saying that you have to get everything under control, like what is allowed, what's not allowed, where are you in the road of trying to solve the problem. You can't lose track of yourself. If right now, if the original function was defined at 0, 0, if it was, then when I multiply both sides right now by x cubed y squared, I would have to make a note, x can't be 0, y can't be 0, and then I'd have to go back and revisit, well, what if it is x is 0 and y is 0? I'd have to talk about that. So I just want to kind of bring that up here, but do you understand why I don't have to worry now? Because the original function is undefined at 0, 0. Yes, the original function, we said we couldn't plug in 0 for x or y, so we don't have to worry about it ever being x ever being 0 or x ever being, or y ever being 0. All right, so multiplying both sides by x cubed y squared, and same thing over here, x cubed y squared. And you know what? Can we get rid of those 2's? They're kind of bugging me. All right, what do we get? X to the 4th y squared equals 1. So does that mean I can say x to the 4th equals 1, y squared equals 1, and then solve the 2? Hell no, you can't do that. Don't do that. That you can only do that zero factor property, right? 2 things multiply to be 0, you can set them both to 0. Two things multiply to be a number, do not do that, right? Okay, I'm kind of at a standstill now, all right, because there's not a lot I can do with this. It just looks better, doesn't it? All right, so let me go to the other equation and do the same exact thing. If I do the same exact thing, what will I get? What do you think I'll get? Y to the 4th. So dot, dot, dot. We should get y to the 4th x squared equals 1. Y'all agree? We did the same sort of approach. Then what? 1, 1 seems like it'll work, right? Is that the only one, though? -1, -1. Okay, so you're doing that just by a visual inspection, and that's useful. I mean, a lot of times we want to knock those out if we can, but we also have to believe that there might be something we're not seeing. But both of these are equal to 1, right? So can't I set them now equal to each other? All right, if this has to be 1 and this one has to be 1, then they have to be equal. So what I can do now is say x to the fourth y squared must equal y to the fourth x squared. Now do not divide, or well, could we? We could divide now, couldn't we? Man, that's so dangerous though. I don't like doing that. Because I don't want to, I don't even want to show it because it's so dangerous later. We can do it in this problem, but I'm not going to do it. I'm not. I'm just so against it. I'm just going to bring everything to one side and get you used to that. And now factor it out. What can you factor out? GCF. X squared, y squared. What's left? X squared minus y squared equals 0. Okay, and that can factor a little bit more. X squared, y squared. This is a difference of squares. It's x plus y, x minus y equals 0. Right? What are our solutions then? We set each of the factors. These are our factors, right? There are 4 factors. Set each one equal to 0. First one, x is 0, then y is 0. We already know we're going to throw those out, right? The next one is x equals negative y. The next one is x equals y. That's what we get when we set each of those equal to 0, right? We chunk these two because those are not in our domain of our original function. So all I know is that either x must be identically y or they must be opposite in signs. So how can I figure out what they are? I mean, like, am I saying that if x is 2 and y is 2, that would work? 3 and 3 would work? Or if I use 2 and negative 2, it would work? I'm missing something. Remember, we had a condition up here, didn't we? We had this condition. We said we could not solve this, right? We couldn't solve this because I have 2 variables in one equation. But now I have a relationship between x and y, don't I? In my 2 solutions. I know that x must be y or x must be negative y. So go back to either one of these equations, doesn't matter which one you use, and plug in these 2 things. So first, if x equals negative y, then I'm using this one right here. X to the fourth y squared equals 1 becomes really what? I'm replacing, let's replace x with y squared. And what would this become? Y to the fourth? It's still positive though, right? So that whole thing becomes y to the sixth equals 1. So that means y must be plus or minus 1, because you would take the 6th root on both sides. Yes? Now, let's try and get our heads around what we got just in this line. Y can be 2 things, right? Y could be 1 or y could be negative 1. But what does the x have to be? Well, no, we haven't looked at that case yet. See, I said if these are opposite, right? If these are opposite, then this is what this turns out to. Y must be 1 or negative 1. Now, if y is 1, what's x? Negative 1. If y is negative 1, what's x? The opposite, positive 1. We've got 2 of the 4. Do you see that? Now, to get the other 2, we have to look at the other condition, which we just did this one. Let's look at this condition. What if x and y are the same? Again, I'm trying to fit this all on one page. If x equals y, then x to the fourth y squared equals 1 turns into, again, y to the 6th is 1, which means y is plus or minus 1. So we get the same result at the end, don't we? But it's the relationship on x and y that's different, so our 2 points will change. We'll still have y coordinate 1, y coordinate negative 1, but now our x coordinate is what? Exactly what y is, instead of the opposite. So if y is 1, x is 1. If y is negative 1, x is negative 1. And we have our 4 points, don't we? Wow. All that work for the 4 points. Now we need to compute D on all 4 points. I'll do D for 1 point, and that's it, and leave the rest for you. I can't believe we're almost out of time. I'm kind of disappointed. I mean, we're halfway through this section, because, well, all right. Should I do D? I'll do D. I'll stick it in right this little spot right here. Let's do D of 1, 1. Okay, what's fxx at 1, 1? Remember what this means, right? So 8. And then what's fyy at 1, 1? 8 again. Minus what's fxy at 1, 1? 4, and then squared. And that's bigger than 0, right? That's 64 take away 16. It's bigger than 0, and my fxx is positive, which means I have a local min, right? Local min. All of them will work out the same way. So local min. Here's what they are. It's 1, 1, 3, negative 1, negative 1, 3, negative 1, 1, 3, and negative 1, negative 1, 3. Yep. All right, I'm not going to do this one, but the answers are here. 1, 1, 1, 0, 0, 0, 2, 0, 0, 0, 2, 0, and 2, 2, 0. We've got, this is a cool one, we've got a local max, and we've got 4 saddles on this one. Local max and 4 saddles. Now, if I were doing this, and I need to get fx, fxx, fy, all those, I would actually multiply this out first. Like I would expand it and make it a nice polynomial and then just do term by term differentiation instead of doing product rule. It would be a lot easier. And let me see, the algebra of that one. Yeah, yeah. I mean, I'm just saying if I were doing, I would multiply it out. Just, let me see here. I'm not going to ask you to turn that in, okay? I would just go home and do that one. Because the fx, setting f partial of f with respect to x equal to 0 and partial of f with respect to y equal to 0 is a little bit involved. I mean, there's just, I think you've seen, there's just some algebra you need to make sure you're comfortable with and take some time to practice it. Now, we have a midterm coming up in a week and a half, right? There's some problems that I gave you that I said you could turn in for that sheet for extra credit, right? Throw this one into the pile. This is, now it would be separate. You would turn this in separately, okay? As its own bonus question, this one right here. Now, if you look at this, it's in your notes, so it actually has the answers, okay? But it's actually, there's something in this problem that is very subtle that I don't know if any of my students in the whole time I've been teaching this and giving this example, no one's ever found what I'm talking about, okay? But there's something happening in this problem. These are correct, okay? But it's not, that those aren't all the answers. There's more answers. So mess with it, do what you can with it if you want for bonus, and feel free to come and talk to me about it, because if you do it correctly, you'll notice you're going to run into something, and yeah, you'll see. There's actually, yeah, there's more to this problem. There's something very interesting happening in this problem that you can kind of see, well, that's just the limitation of the graph itself. Let me see here. Yeah, that's just a bad graph. That's not it. It's hard to see it here. But the algebra should alert you to something. All right, there's something in the algebra that you have to take account of, and you're either going to see it or you're not. Now, if you turn it in and you don't see what I'm talking about, I'll still give you some credit for it, okay? But it's a bonus question because there's an idea in here that extends beyond what I've talked about in this class. Yes. That's it. That's all I was saying. It'll cover what? That sheet. Oh, is that what I said? I didn't say it was bonus? Okay. So all those problems, we're going to replace your lowest take-home quiz grade. Yes. That's right. Yeah, because it's a lot of problems, right? Yeah. That's what it was. Okay, and this one will be bonus then. All right, now look, I understand we have a few more minutes. I just want to talk about what we're going to do next class. I will go through all this again. Don't totally turn me off here. But I want you to see the difference between what we did today and what we're going to do next time, because there's a subtle difference, but it's a huge difference. If what we did today, we were just looking for local maxes and local mins, and we never restricted the domain, right? We never said, okay, take this surface and just look over here and tell me where the highest and lowest points are. We just said, look everywhere and tell me where the highest and points are, right? Highest and lowest points are. But if we restrict the domain, things become different. So check out this function right here, right? No big deal. Right there, we could probably find a saddle point, right? But now what I'm going to do is I'm going to restrict it. I'm going to look at a triangle on the ground and restrict my domain to just that triangle. Oh, wait, was it a triangle? No, it wasn't a triangle. It was a rectangle, sorry. Oh, here it is. Let me get to the beginning of this. Okay, so what if I say, instead of plugging in everything and then getting the surface, right, just go into this triangle, just plug those points in. Then here's my triangle in two-dimensional space. There's the triangle in three-dimensional space. That's what's getting plugged in. When I plug those in, well, here's the entire surface if I don't restrict it, right? Yeah? If I restrict it, I'm going to kind of make it a little. If I restrict it, damn it. Can y'all tell that that green part is part of the surface? Yes? And if I look at it from straight above, and I will pull the rest of the crap that's just getting in our way out, then can you see that that green thing is exactly the map or the image of that triangle into the surface? It's just that triangle up to the surface, or sometimes it goes below. Do y'all see that? And if I look at just this green thing, and let me take the domain out of there because the domain is probably getting in our way too visually. This green thing is now its own like miniature surface, but it has boundaries to it, doesn't it? And now if I say what's the highest and lowest points on this, that's totally different than you being allowed to look everywhere. You can now have an absolute maximum somewhere here. In particular, you have two highest points and two lowest points. Do y'all see that? And we need to be able to find them. It's going to be a task for us to do it. The analogy is that what we did today is very similar to what we did in Cal 1, where we just took a function and we didn't restrict its domain. And we said, okay, find the highest and lowest points, right? That's what we did today. Local max, local min. But in Cal 1, when we restricted this, we said now, restrict it on a closed interval, right? Between A and B. If I ask you what's the highest value, what's the maximum, the absolute maximum of this, it'd be this point up here, wouldn't it? Which is happening where the derivative is 0, and that's fine. But the lowest point's here, right? The lowest point is actually occurring at an endpoint, right? So you would have never known that. Had I allowed this function to continue, that blue point here would have been irrelevant to us, wouldn't it? But by restricting it and closing it, now that point actually becomes the lowest point on the entire graph. And that's where we'll be here. We'll be sitting here and going, crap, man, this point used to not matter, but now it does because I'm restricting my surface. So how are we going to do it? Well, come to class and we'll talk about it next class, all right? Next week. Let's see, if there's homework for this, you might be able to start. Yeah, your take-home quiz is due. What is your take-home quiz? Can I see someone has that take-home? I want to make sure you can do it all now. There you go. You can do number 3. Number 3 is just like what we did today. The algebra might be kind of messy, but... All right, 11.7. This is page 675. And 3 through 13. I'd say 3 through 11 is good. 23, what's that? 675, yeah. 3 through 13 is fair game, or 3 through 11. The 20s problems are what we're going to cover next class, so if you look at them, you'd probably be a little stuck on those. Everyone have a good weekend.